Okay, so we can start. Today's topic is curve fitting. Curve fitting. It is part 5 in the book. Okay, so this book talks about two different types of curve fitting. First type is the following situation. Let's say that you are measuring something. And that measurement has some error. Okay, you cannot measure it precisely. It has some error. Okay, so you are measuring some quantity. You call it y as a function of x. Okay, you are measuring it at different x. Okay, what you can get is some scattered points. Okay, because of error of measurement, the actual value may be scattered. Okay, in that situations, very often you have to figure out what is a functional form of this. What is the functional form of this one? Yes, there are errors. They are scattered, but what is the underlying functional form? Okay, which is to say, what is that curve? What is that curve that approximates the behavior of these points as a function of x? Okay, what is that curve? It's some curve which kind of approximates all of those points, right? So the task of finding that curve which approximates the functional form of those points is called a regression. And one particular form is called least squares regression. All right, so that's the one form. Here it looks like a linear, right? It looks like a linear. It doesn't need to be linear. In the most general case, it doesn't need to be linear. It can be exponential, it can be quadratic, it can be polynomial, okay? And on top of that, here it's one-dimensional. This function y depends only on x. It doesn't need to depend only on one variable. It can depend on more than one variable, on two variables. Sometimes maybe you need to fit a plane in three-dimensional space, okay? So that's a curve. This is one form of curve fitting. Another form of curve fitting, which this book discusses, is what is known as interpolation. And interpolation is the following problem. Okay, suppose you measure y at different values of x. Okay, you measure it here at x equal to this guy. You measure it at this point. 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 And the values of y, let's assume they are precise. Okay, so next value can be here. The third value can be here. And it can be here, it can be here, and so on. Okay, so you measure this quantity y at these different points. So this is the only data you have. Okay, that's the only data you have. Now someone may ask you, give me the value of y between these 2 points. Based on the data which you have, give me the value of y between these 2 points. You do not have the data really there because you have it here. You don't know the value exactly here, right? But someone asks you, or suppose you need that value. And that problem is called interpolation. Interpolation is a problem where you calculate a curve that passes through all these points, and in between they have a certain behavior, such that based on the form of this curve that goes through all these points here, so that you can predict or you can get the values between these 2 points, okay? So let me repeat. Here you have some discrete data points, and you create a new curve, some function, which goes through all these points. They go through these points. They pass through these points. And once you know this function, you can calculate the value of that function between these 2 points. That problem is called interpolation. Interpolation. Whereas here, in this regression problem, this line, which characterizes functional form of all these points, doesn't need to pass through every point, right? This curve, this line, which is described as a behavior, doesn't need to pass through every point. In this case, there are a lot more points, and you want to predict some kind of average behavior of those points. That's regression problem, or curve fitting. Whereas here, you want to predict the values between these 2 points. In some situations, you have to predict the values outside of the region where you have the data. Okay, suppose your data starts from this value to this value, right? What if someone asks the value outside of this range? That problem is called extrapolation. Extrapolation as opposed to interpolation. Okay, in some communities, in some disciplines, when you say curve fitting, people understand this problem. Okay, not that problem. That problem is specifically referred to as interpolation in some contexts. But in this book, they define both of these problems as curve fitting. This particular form is regression, and that particular form is interpolation or extrapolation. All right, so today we start talking about this problem. Okay, we start talking about this problem. So we have some data points, and we need to predict, we need to calculate what is the functional form of that data. Okay, a lot of data with maybe errors in the measurements, and we need to predict what is the functional form of that data. Okay. In another way, we need to fit different functions to represent this data. And the simplest function you can fit is linear function, right? Some straight line. You can fit some straight line. So in this case, it looks like a straight, right? It looks like a straight line. So we may try to fit a straight line here. That's the simplest possibility. And that's what we're going to discuss today. We learn how to fit a straight line. Some of you already did it. For example, in Physics 1 laboratories, some of you already did it. Okay, so, and because most of you know, and because it's such a simple problem, we introduce a lot of ideas which we will be using for a more complicated case in this example. Okay, later we'll discuss more general polynomial fit. Okay, here we are looking at straight line fit, and straight line has a simple form: y is equal to some a0 plus a1 x, right? So it has only two free parameters. But later we'll learn how to fit, for example, polynomial, which has more difficult, more complicated form, a2 x squared, for example, and so on and so on. Okay, but today we started with this problem where we try to fit a linear function, and that problem is called linear regression. Linear regression. All right. So we have some data points again, and we need to find such values of a0 and a1 such values that this line will be the best fit, Okay, the best fit. So we have to quantify what it means to fit the best fit. Okay, in which sense it is the best. Okay, in which sense it is the best. All right, if we draw this line, so we have these points. Let's call them xi, yi. Each point is xi, yi, okay? And where I goes from 1 up to n. So we have n points. All right, so when we're drawing this line, it doesn't pass through every point, right? It will have some error. It will have some error, right? It will have some deviation from each line, each point. This line has some deviation. It doesn't pass through them. So let's divide that. That is just, let's call it ei for each point will be just the value of y for that point minus this function, right? a0 minus a1 xi. Okay, this is error for each point. So the first option we can think about is, let's say we want such a straight line in which the sum of all the errors will be the smallest. Okay, that may be the simplest thing you can think about. Okay, let's look at this. Sum I from 1 to n, ei. Okay, that's just sum of these guys, yi plus minus a0 minus a1 xi. What if we try to minimize this quantity? Is it a good idea or bad idea? It's a bad idea. And we can see it in the case of 2 points, for example. Suppose you have only these 2 points, okay? You have only these 2 points, and you are trying to fit a line, okay? And obviously, a straight line that represents 2 points is the one which goes through those 2 points, right? It's, in this case, it's clear, unambiguous. The line which represents best 2 points is the line which goes through these points, right? But the thing is that when you minimize this quantity, when you try to minimize this quantity, any line that goes through the midpoint, for example, this line, will have minimum E, minimum sum of E. Okay? So this is a bad idea. This is a bad idea. All right, second option. What if we minimize the absolute value of this case? What will happen in this case? Any suggestions? It turns out that's also not such a good idea. For example, if you have these 4 points, say this one, any line between these two lines will have minimum of that. Okay? So that's not even a good idea. It turns out the best idea is the following. We have to minimize sum of the square of these guys. It turns out if you build such a line in which this quantity, which is called SR, this quantity is a minimum, it turns out that line is actually the line which represents best fit. Under certain assumptions, you can even prove it mathematically, assuming that under certain assumptions, that is, if these points are scattered randomly with Gaussian distribution, and if the values of x are known precisely, you can show that the line which is fitted according to this mathematically is the best line, or the most probable line. You can show it even mathematically. Okay, so it turns out this is a best measure. So we have to try to minimize it. Okay, all right, let's try to do that. Okay, last 2 lectures we discussed minimization of functions, right? So here is a function which we need to minimize. Okay, this is a function which depends on these 2 free parameters, this one and this one. So it's a 2-dimensional minimization, right? We discussed some methods. So do we need to use those methods or not? Exactly. This is a super simple function, right? This is a parabolic function. This is a parabolic function. And minimum of that parabolic function, we can calculate it easily, right? And let's do that. Okay. So we have 2 parameters, a0, a1. So derivative of SR with respect to dA0 should be 0, and dsR dA1 should also be 0. These 2 conditions gives us 2 equations from which we can find a0 and a1. Very simple, right? Idea is very simple. All right, let's look at dsR dA0. That will be minus 2 sum I from 1 to n yi minus a0 minus a1 xi, right? So that is equal to 0. dsR dA1 is equal to minus 2 sum from I to n yi minus a0 minus a1 xi multiplied by xi. That should also be 0. Okay, so here are my 2 equations, and from this I need to find a0 and a1. This is really trivial to solve. System of 2 equations, 2 linear equations with 2 unknowns. We can solve it easily. I'm going to just write the final result, okay? The final result. If you write the final result, a1, it turns out is just this guy, and multiplied by sum, where sum is from I equals to 1 to n, xi yi minus xi yi xi squared minus sum over I xi squared. All right, this is a1, and a0, it turns out, is just y minus a1x, where y bar is just arithmetic mean of y's. It's the same for x. All right, so these are the values. All right, it turns out it's extremely simple. So if you have n points, xi, yi, endpoints. The best fit, the best straight line is the straight line for which a1 is equal to that, a0 is equal to that. Both of them you can calculate easily. You just have to do loops, right, over this. That's it. You have it. Any questions so far? All right. So suppose now we made this fit. Suppose we made this fit. Let's try to measure how good is this fit now. Which is to say, how is the distance, how large is that average distance or typical distance between this line and these points? Some kind of average of these distances between this line and these points. Okay? And there is a quantity called standard deviation for that. It's kind of standard called quantity. That's why it's called standard deviation. And let's look at that. Let's look at this quantity. Okay, let's do it here. Okay, so you have these points, xi, yi, where I goes from 1 to n. Then you have average y, right? So you have some average y. So let's say this is average y. So this is average y. You can calculate a deviation from that average y, right? St, let's call it st. Sum I from 1 to n, yi minus y bar squared. Okay? We can calculate the deviation from this average. It's not a deviation from this line, it's deviation just from this average. Right? This is just that. There is a quantity called standard deviation. And this is defined like this. We call it sy. Sy will be st divided by n minus 1. Okay? St divided by n minus 1. That's the definition of standard deviation. That standard deviation is a measure, some kind of average measure of the deviation between this mean line and these points. Okay? Some kind of average of those. It's a standard deviation. It is divided by n minus 1. This is number of the degrees of freedom. Okay? It's a subtle point, why it's n minus 1. It is related to the fact that we have a n minus 1 degrees of freedom, in the sense that here we have n points, right? We have n points. But when we calculate y bar, we use those n points. So this y bar depends on those n points. So this quantity, in some sense, has n minus 1 degrees of freedom. Not all of them are independent. All of these terms are independent. One of these quantities are dependent on the rest of the quantities, which is related to the fact, simpler fact, that you cannot define average deviation of a one point. Okay, if you have just 1 point, can you define a deviation of that point from itself? You can't, right? It is related to that fact. That's why you have n minus 1. All right, this is now deviation from this mean, average. We are looking at the deviation of these points from this average. Now, accordingly, we can define deviation from this line, of each point from this line, which we calculated. It is defined in a very similar way, in a very, very similar way, where instead of y bar, we'll have this y. Okay, the actual straight line. All right. What was the notation which I used? Okay, in that case, we call standard deviation a syx, and that will be sr here instead of st, and n minus 2 now. N minus 2. Why is n minus 2? So number of degrees of freedom, I'm saying, is n minus 2. Why it became n minus 2 here? It became n minus 2 because this curve has two free parameters. And we use more information to calculate those two parameters. That's why we have to divide by n minus 2. All right, so this is a standard deviation. So this guy is a standard deviation, which is an average kind of a measure of the distance between these points and these lines. Okay, this one standard deviation from that fit. This, on the other hand, is a standard deviation from the average of all those points. All right, now using this quantity, now we can define one quantity which gives an idea about the quality of the fit any case, for any situation, okay? And that's called correlation coefficient. Correlation coefficient is R, where R squared is defined like this. ST minus SR divided by ST. And R is called correlation coefficient. All right, let's look at what is the meaning of R. So suppose R is equal to 1. In that case, that means, okay, that happens when SR is equal to 0. SR equal to 0. SR. SR is a sum of the residuals from this line under all these points, right? Sum of the squares of errors. So this corresponds to perfect fit, right? Because let's remind ourselves, SR is a sum of EI squared, right? I from 1 to n, which is sum I from 1 to n from points yi minus a0 minus a1 xi squared. Okay, when this is 0, it means a fit is perfect. All right, another option is another extreme is R is equal to not 2, 0. What does it mean? It means that SR is equal to ST, right? What does it mean? Just a second. What does it mean? It means that this SR is not better than ST, which is deviation from this line is not smaller than the deviation from the mean. So our fit is not giving us a better result than the mean. We could as well take as the mean. All right. You have a question? ST, exactly, ST, sorry. Okay, so this is how we can do linear regression, and this is how we can judge about the errors in our regression, in our fit. Linear. So it's a linear regression. Okay, linear. It's a little bit restrictive. Linear is a little bit restrictive. Okay, because not everything is linear. There are situations where things can be exponential. For example, in some situations, population growth can be exponential population growth. Something may grow. Something may exponentially damp. For example, damped oscillations amplitude decreases exponentially. If you have instability, some kind of instabilities, amplitude may grow exponentially. So exponential function is very common. Power law is very common. And another common situation is something grows, but then stops growing. For example, population grows. Population grows, but then it reaches some limits, maybe resource limits or something, then growth stops. Or some instability grows, but then when the resistivity becomes large, for example, if you throw something, it starts accelerating, right? But then at some point it reaches its maximum velocity, terminal velocity, and then velocity doesn't grow. So these are some examples of very common situations. And it turns out some of those common situations can be formulated as a linear regression, as we will see in a bit. Okay? Sorry? Exactly, as we will see. All right. Okay, so we learned how to do linear regression, how to fit the data of this form, which is a straight line, to some data. Okay. Very often, the data can be of exponential form, right? Can be something like this, something which grows exponentially or decays exponentially. All right? Y and x. That can be expressed as some alpha 1 multiplied by e to the beta 1 x. Okay, this can be formulated as a linear regression problem. How? We just transform it. There is one-to-one correspondence, as someone pointed out. Let's take a natural logarithm of this guy. It will be just alpha 1 multiplied by e beta 1 x. That is just equal to this guy. Okay? This is just equal to this guy. Let me rewrite. Okay. Okay, very good. Now, I will call this guy, I will call y tilde. This guy I will call a0. This guy I will call a1. So this will have this form. Y tilde is equal to a0 plus a1 x. Now, if initially I had these points, some xi's and yi's. From this, using this transformation, I can get yi tildes and xi's, right? Now it's exactly a regression problem which we discussed, linear regression problem we just discussed, which means that we know how to find a0 and how to find a1. All right, if you have a1 and a0, my beta 1 is just a1, because beta 1 is a1, right? a0 is alpha logarithm of alpha 1, from which alpha 1 is e to the a0. All right, I found it. I found all these parameters, which is to say, I fitted this guy to some points which has a bit exponential behavior. Okay, very good. Second example is a power law. Power law is slightly different. It has this form. It goes through 0. So your data can be something like this. We try to do the power law, which is alpha 2 x beta 2. This is the form. Again, we can transform it. In this case, let's take base 2 logarithm of this guy. Log y is equal to log alpha 2 plus beta 2 log x. Very good. I call this guy y tilde. I call this guy a0. I call this guy a1. And this guy is x tilde. Again, what do I have is y tilde is equal to a0 plus a1 x tilde. All right. Again, my starting point, I had xy's and yy's. I transform them to y tilde i's and x tilde i's. I have n of them, from which I can find a0 and a1 using this linear regression, which means that alpha 2 will be then 10 to the power a0, beta 2 is just a1, and that's it. I have both of these parameters, and which means I can draw this line. I have the parameters of that line. Done. I did power law also. There is a third option. There is a third option, which we'll consider, and that's called saturation function sometimes. It is something which behaves like this. This is your y, this is your x. It increases and then saturates, grows, saturates. It grows, but then stops growing. Okay, it's a saturation function. One particular form which we are going to consider is this one. This one will be alpha 3 x beta 3 plus x. This is the form which we consider. Okay, can everybody see what is in that part? All right, let's try to solve that. Okay, I'm going to invert that. I'll write it in this way. 1 over y is equal to 1 over alpha 3 multiplied by beta 3 over x plus 1. Right? Exactly. All right. So this will be my y tilde. Y tilde is just 1 over y. X tilde will be 1 over x. My a0 is 1 over alpha 3. A1 is beta 3 over alpha 3. Again, I have a problem with this form now. And I have my points again accordingly. Y tilde I, X tilde I. And I can do regression, linear regression, and find A0, A1. And find parameters alpha 3 and beta 3. And draw this line. Okay? So it turns out some of these common functional dependencies, exponential power law, can also be formulated as a linear regression problem. Okay, so this is it for today. That's all I wanted to say today. Next time, we'll learn how to fit polynomials. Polynomials have more terms than only two. There is square terms, cubic terms, and so on. We'll learn how to do general polynomial. That's one. Second thing we'll learn is how to do the regression in multiple dimensions. Here, it's one-dimensional, meaning that y depends only on one variable x. What happens if we have more than one variables? That is also what we're going to discuss next time.